Yeah, thank you everyone for coming today to our one of I think two in-person NPAs this semester. So today we have Professor Rene Bellwied with us. He's a MB Anderson Distinguished Chair of Physics at University of Houston. Rene received his PhD in nuclear physics and chemistry from Johannes Gutenberg University in Germany. Then he was a Dorlihan Fellow of the Humboldt Foundation as a postdoc at Stony Brook University before becoming a professor at Wayne State. After 20 years at Wayne State, he then became a full professor at the University of Houston in 2010, where he has been since then. He was a founding member of the STAR collaboration at RIC, where he was a project manager, deputy spokesperson, and physics working group convener. Then he joined Alice at the LHC in 2010, where he did a lot of things, including being an EMCal physics coordinator, and he was also an Alice USA coordinator. In addition to his work in collaborations, he served on the policy committee of APS and the chair of the Texas section of APS. Yeah, so thanks for being here, Renee. Renee will be talking today about from the initial to final state quantum entanglement and relativistic particle collisions.
Wow, thank you. Thanks a lot. Thank you.
Yeah.
Should I do it here or should I stand there?
And you can stand if you want. Yeah, I think it should work. So, and they can see us from over there.
I brought the jacket for you guys, so I'm going to show it up.
Yeah.
Here probably, so that I can see my own slides too. So thanks a lot for the invitation. I'm going to talk to you about some people might call it a pet project or something. It kind of reminded me that I'm getting to that age where you talk about things that are a little different. Reminded me when Jack Sandweiss started looking for strangelets. So, you know, at the end of your career, you're doing something that is a little bit outside of the ordinary. This goes back to a conversation I had, and I want to mention this because, you know, many of you have been to the winter workshop and some of you have not yet been to the winter workshop, but they should come to the winter workshop because that is based on a conversation I had with Reinhard Stock at a winter workshop in Thailand, which was a very exotic place, very nice. But the main thing with winter workshops is that you can sit down in a nice place and you talk about physics in a different way than you talk about physics when you're in your university or so. And we had a conversation where I tried to understand the difference between the Herbig model and the PYTHIA model. And he got very much into the detail of what the high energy physicists called the popcorn principle in order to make clusters out of quarks. And I had a hard time, and he had a hard time really understanding how some of these event generators are trying to mimic fundamental quantum mechanical principles that should be there when we talk about our interactions, but that are often either ignored or parametrized in a way that is not really obvious to us what's happening. So I wrote a little paper about this in 2018, and then I recognized that there was a lot of work done in 2017 that I wasn't aware of at the time. And now when I thought about coming to Yale talking about it, it's like me as a German trying to explain to my Italian wife how to make pizza or so, you know. So I'm in the lion's den right here. Keith has written paper about this. Thomas has written papers about this. One of the papers that I will refer to over and over again is this 2 Kajev-Ulrich paper. And that's obviously the stuff I'm talking about, but I tried to put a kind of an experimentalist spin on this from my point of view, and B, trying to understand a little better what the quantum mechanical principles are. But in any event, if you want to work your way into this, all the Kajev papers with collaborators are interesting. And then Raju did a sabbatical in Heidelberg, worked with Stefan Flöschiger and Berges on this and wrote 2 of these papers as well. And they just give you an input. And I think it's interesting that, and I come to this later on, that part of the groups looked at this in what I would call a transverse way, so transverse entanglement inside the proton. And the other part of the group looked at this in a longitudinal way, namely entanglements through string fragmentation and the particles coming out of a string being entangled. Now, quantum entanglement is a topic that you know goes over many different fields of physics, and generally when you have quantum entanglement in your title. People get interested in this and feel like this is something that we should think about. I depicted here a little bit by looking at effectively the three valence quarks in the proton being entangled, and then later on leading hopefully to an entanglement from the initial state to the final state, where the particle production in the final state could be traced back to the entanglement that you're having in the initial state. That's the general idea of this talk. And some of it in particular, when I go away from simple proton-proton collisions into heavy ion collisions, is highly speculative and probably not true. So I just want to present it to you as an option, and then you can look at it and you can see whether there's something that might be useful about it. What I think ultimately it's almost a science fiction idea when you translate it into the heavy ion system. But I had so many interesting discussions that led then to some more substantial ideas in the proton-proton system that I felt it's worthwhile to keep talking about it. And you saw the first talk I gave in 2018 at the winter workshop, and I gave one this year at the winter workshop. And
But then we want that.
John, give it and John.
Okay, so now can y'all see and hear us?
We lost the talk.
Yes, 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 let me, oh, we lost, you're right, we lost the projector.
No, I just keep saying.
This isn't the one that you tried.
Many times you have to free up
This
this
is the one you tried.
space.
Well, I have a
Screen on.
Why did we lose this?
Austin is saying it looks larger than the lab.
Okay.
So if it helps, the video and the Zoom seems, the sound seems to be back.
I'm trying, yeah.
Could I already ask Anita?
We'll still give you the time.
Okay.
We'll still give you the time, don't worry, I think.
Were you about to continue again? Were you about to continue again, or can I ask a Neve question?
Yeah, go ask the next question.
So when we start out in undergrad, we always have many quantum courses, and then the moment you dive indeed, it's a little bit in this abstract as well. When you then go into particle physics, you kind of immediately forget about everything quantum, right?
Right.
Is there any reason why we never think about anything quantum-like? It's a bit of a bold statement, but I mean, we do kind of do, I mean, the whole production stuff is all quantum in a sense, but I mean, the spooky actions thing.
Well, I mean, I think if you can't describe the system as a, you know, as a point source on point source in vacuum interaction, then you don't need the quantum stuff, right? So I'm pointing that out on the next slide, which is essentially the difference between E plus, E minus, and PT, where the fact that you are taking a constituent that is entangled and do an interaction, it's not a point-like interaction anymore. And then the many-body interaction starts to play a role, and you have to take it into account. Whereas if you just do E plus, E minus, you might not need, right? At least not in the transfer. So it's a good question, because if it's still generating longitudinal strings and the string fragmentation is a quantum process, then you will still need, right?
Yeah.
But ultimately, string fragmentation, the first order PYTHIA, was quite successful in describing it without any quantum interactions. I think the breakdown really came when you finally got high energy proton-proton interactions, where you can drive up the multiplicity of the final state, and you see actually that it makes a difference. You know, so the paper I'm pointing to on the next page is the one that my group was very much involved in the last 2 years, which is the non-universality of charm fragmentation in ALICE. And there you see already, I mean, whether you can link these two things in the end together, you have to decide at the end of the talk, right? I mean, because we're talking about different quantum mechanical effects, can they all be simply attributed to entanglement? Because also, honestly, when you talk about entanglement, most people think about spin and nothing else, right? So any spooky action at a distance or something is defined by the spin system. What we're talking about here is entanglement of other quantum mechanical properties. So is that really the right language? Am I applying it right? That's the thing that we should discuss.
Sorry, your talk got stuck in some weird mode because of the,
So was anyone else on Zoom?
Yeah, there were people.
what was it called again? What was it called again?
Well, you copied it over, right?
Yeah, I did, but
It's called Yale
It's on
Entanglement.
the
Could be
desktop.
Yale. Should start with Yale.
Oh, it is? Okay.
Yeah, I'm not gonna get this either.
Yale Entanglement, that one.
Sorry, I got stuck in some weird mode. So it like wouldn't let me play it.
He says it's okay.
Can see that screen share screen. So two. Share. Okay. There we go. Okay, sorry.
So I can't see it here, but I can see it there.
Yes. And then you
Okay, now
use
just say it. I mean, I can sit here then if you want,
whatever you,
because then I have to really see it.
sorry about that.
I'm gonna sit over here.
Yes,
If
there
that's
are
okay.
people,
Is
there are
that
like
okay?
4 or 5 people connected.
Yeah,
Yep.
But then I can see it.
Sorry, yeah.
Thomas is wondering what bad things you're saying about his paper that you disconnected.
Someone emergency disconnect.
Yeah, someone from the Yale up like.
You're like,
Well,
"Thomas, you
you know, Dima is on it too, so yeah, anybody could disconnect me at this time. Right? So this was one of my favorite papers, one of the best papers written in the last 2 years by Dima and Thomas. Oh, and I come back to this. You know, I think this is obviously one way of looking at it, and it's a way that we're trying to adopt right now also in the other experiments. But there might be other interesting measurements that are coming up now that are a little bit more go deeper into the structures, I would say, of a proton-proton final state. And I discussed one with Thies this morning, which is the elliptic flow measurements that could potentially also lead to something which is very interesting. Let me go back to the motivation, and we just talked about this even with Mike's question, that the proton-proton interaction is pretty complex, right? And it has these things that we're now trying to understand better, in particular based on LHC measurements in proton-proton, very detailed LHC measurement. And if you look at some of the papers that have to do with flavor dependencies that came out in the last few years, we had the Nature Physics paper of the strangeness enhancement in PP in step by step. We have the non-universality paper of the fragmentation of charm. All of them lead to some kind of a question of whether not only the simple number of particles is affected by the complexity of the interaction, but also the flavor and the color that comes out of the interaction. And there are many, many different ways of looking at this in string fragmentation models, but ultimately, at least as an experimentalist looking at this from the outside, every time somebody talks about parametrizing multi-parton interactions or parametrizing color reconnection, I feel like these are fudge factors. Now, these fudge factors have a physics meaning, and I think when you use PYTHIA, it's very important that you work your way into these physics meanings, because they have potentially some interesting physics in them, but the dynamic of them is still driven by a parameterization that you put on in order to fit your data. So there's not really that connection back to the first principle that you would hope for. In addition to the proton-proton being much more complex than the E plus E minus, the initial state, therefore, is also much more complex. You have a parton distribution function that clearly at very low X saturates. You have models like the color glass condensate. And one thing, at least that's how I define parton-hadron duality, that always baffled me, is that very early on in the heavy ion collisions, some of our theorists made the discovery that the density of gluons in the initial state is equal to the density of hadrons in the final state. So this is very peculiar to me, and I never really understood it. And that's what I call parton-hadron duality. There are other definitions of parton-hadron duality, so you should not necessarily follow that. But if you calculate a gluon density in a central heavy ion collision, you get about the same dn dy that you get when you look at a charged parton distribution, charged hadron distribution in the final state. And that's something that also could be potentially a hint at what I'm talking about. The other problem in heavy ion collisions that always baffled us, and we kind of found some explanations for it along the way that are more or less exotic, is the idea of fast thermalization. So you cannot thermalize fast enough based on energy distribution through particle collisions, even parton collisions. So the fast thermalization, which is clearly a prerequisite for hydrodynamics, is something that is not well explained on first principles. There's also seemingly, if you apply the same model, at least in terms of particle distributions, to E plus E minus, you see thermalization also in E plus E minus. And then on top of this, as of late, the idea that a very loosely bound state can be thermal. That means you have 100 keV binding energy particle in 150 MeV heat bath, and it does not dissolve. It essentially keeps its entropy per baryon ratio, which is something that I will come back to, is also baffling. There are some ideas, some detailed balance calculations by Olinichenko and company that seem to explain it, but I think there are a lot of shortcuts were done in this calculation that might make it not very realistic, at least from my point of view.
So Renee, just on that, I mean, how do you know that it exists even in the thermal bath and not just the product of it in the very end?
Well, I mean, to some extent, if you believe in the thermal bath, then the thermal bath cools, right? If you want to just have coalescence at the end of the thermal bath, then the temperature, the slope parameter of that spectrum should be 100 MeV or 90 MeV instead of 150 or 160 MeV. So the distribution is very much in line with the distribution of protons and neutrons at the chemical freeze-out. Now you might have ideas where chemical and thermal freeze-out fall on the same line if you fold in the resonances like the Heidelberg group has done. But ultimately, even in that case, the temperature is high, right? The temperature is 150 MeV. And you would have to do what people did, you know, Florkovsky, Rafalski worked for like 20 years ago on this idea that you have essentially sudden freeze-out, right? No more rescattering. But if you have any rescattering process, that loosely bound state should be gone, right? So I feel that falls into the same line of argument. And I come back to that because if you drive this all the way to the extreme, which I will do at the end, then I will say actually that a string fragmentation can generate that system right out of the fragment. It can generate an entangled nucleus. And it does not need any coalescence or anything else in order to make that state. That state is directly generated in the fragmentation. You can think about that already. Can I make a helium-4 atom out of a string fragmentation? And I'm just bringing this up because Brodsky wrote a paper about this just 6 months ago, and I read it and I was pretty excited about it. So, and then the last point is pretty much in terms of motivation is what Micah says, the necessity of quantum mechanics in a many-body system in general. This is a many-body system, even in proton-proton. It's not a point-like system, and I think that's what drives this a little bit. And as an argument, I want to use now and a measurement that we have done in ALICE as of late, which is the idea of can I take an E plus E minus collision and compare it to PP collision. This is generally done under the norm of the universality of fragmentation. So whatever I measure in E plus E minus, if I apply the same thing in PP, I get the right result. So I can do a superposition, not a superimposition. I stole that from my student. So a superposition of E plus E minus collisions, and I get the PP collision. Yeah. So is that true? And in ALICE, this is very much touted as a difference between a simple fragmentation approach for hadronization compared to a coalescence approach for hadronization. I'm not getting into that too much. I'm just showing you that the non-universality is pretty well established based on this left-hand plot here, where you effectively show now that when you look at how much the charm fragments in a particular hadron, and you compare the E plus E minus results, which are in red and in blue and in green. So these are all EE or EP measurements, and you compare it to a PP measurement or even a P-LED measurement for that regard, you see that the D0 is suppressed and the lambda sub C is enhanced. So that is clearly non-universality. I cannot take the fragmentation function that I measured in E plus E minus and apply it and get the right distribution of particles. There are lots more details that I'm glancing over here, like why is the D0 suppressed but not the D plus or the D sub S. So I mostly want to focus here on the fact that the main meson is suppressed and the main baryon is enhanced in these distributions.
But only when you put two baryons in there, right? EP is fine.
No. These are all Alice data. This is EP here is
EP works. EP is the same as E plus E.
yeah. So yeah, right. So you need yeah.
PP
When,
is the
yeah, I didn't. Yeah. So EP is fine. PP is not fine. Yeah. And then you can go more differential, and you can look at this. And here are two centrality bins for the lambda over D ratio from Alice at low multiplicity and at high multiplicity. And Raghav asked me this morning, well, can I find a low multiplicity PP collision that looks like an E plus E minus? And the answer is no. The E plus E minus are these plots here, because Monash describes E plus E minus very well. Even in the lowest multiplicity min bias, if you want PP collision, you see already an enhancement, but you see also that that enhancement gets bigger and bigger the larger the final state, the more multiplicity you get. And now you ask an event generator model to go beyond the simple point-like interaction, and then they can probably find something that does that. And this is color reconnection beyond leading color mode 2. So now you want to know what each word in this connection means. What have they done in order to push this up to the right level? And I'm going to go back into this a little bit when I talk about the latest approaches to this, but never forget, this is now, what do I have to do to a point-like interaction to make it a little bit more collective, right? And yeah. So how do we do, so going back to what we're actually doing, and what we're doing, and I got this from Dima, is essentially a parton-parton interaction where we ignore the rest of the proton. So it's a parton-parton interaction in vacuum. There are a few disclaimers that make that actually interesting, and you see them at the bottom here. You can, for example, do clustering like Herwig. You can do some patches in DGLAB. You can do parton cascade models, all of that. There was a very interesting paper by Thomas Lappy in 2011 that shows that if you do DGLAB applied on the energy-dependent gluon saturation scale, then you have to take that into account when you calculate what type of clusters you get from the soft processes. So the DGLAB correction to this cannot be applied in an energy-independent way. And again, it's a patch. It's not something that was initially in the PYTHIA model. So what we're doing wrong effectively is we're treating a quark-quark interaction as if it's an E plus E minus interaction, but we're ignoring the connection, the entanglement to at least the remaining diquark. And whether it's two quarks or a diquark is also an important part of this, because only the diquark really gives you the right baryon numbers when you look at PYTHIA. PYTHIA needs a diquark production in order to get the baryons right. So here are just to show you some little explanations on what a PYTHIA model does in order to, if you want, include quantum effects, right? And I broke it down here. It's hard to read, but it's interesting. Mode 0, mode 2, mode 3. There are time dilation constraints that you can put in. And that's an interesting part when it comes to how you treat color, because each color, each mass quark has a different formation time. So you have this effect that you could potentially line up early charm quark clusters with late strange quark clusters simply because of the formation time difference between light quark and strange quark and charm quark clusters. And that plays a role. And that is essentially, folded into these different modes. And you can see how big a difference these modes are making when you, for example, again, look at the baryon to meson ratio in the charm sector as a function of multiplicity in PP. So the Monash tune sits down here, and that is the best tune, right? I just heard from Raghav, there's a better one called the Detroit tune, and I'm looking forward to the Detroit tune. But as of now, I'm happy it's called the Detroit tune, but Monash at the moment is still,
Only because the LHC don't listen.
right. It's the Rick tune, the Rick Detroit tune. Go Detroit. So this is what you would get from Monash if you don't do anything. And then you do color reconnection. The words already say it, but how you do color reconnection makes a big difference on how many baryons you get compared to how many mesons as a function of centrality, as a function of multiplicity. And you see the data, you see the 3 tunes, nobody is super happy with anything, but at least you lifted it away from being completely independent of the final state multiplicity.
But then, so then the mode 2 is the one that described the previous slide the best, right? Is that right?
Well, it's
Or maybe not,
yeah.
Oh, okay, yeah, okay.
It does pretty,
Yeah.
it does, it
But then
overshoots.
kind of misses.
Right, it overshoots tremendously at low PT. This is as a function of PT, it's a little bit more differential, but only for one of those bins. And that bin was at 37, right? So you see at 37, it overshoots tremendously. And, it's depending on what you need from PYTHIA, you can find a mode that describes it. But there's no mode that describes everything. And that's always worrisome, right? Now, there could be a color dependence. But if I need a different mode for strange particles and for charm particles, I'm already getting into maybe the time dilation helps with that. But other than that, I gotta think more and more and more how I describe the quantum effects. And that's mainly what I wanted to show here. The other thing is the problem of generating baryons. So there's essentially 2 processes within PYTHIA that can be turned on and off, which is essentially the junction process, where the baryon number travels with the gluon junction, or the diquark process, where the baryon number requires you to have a diquark-quark formation rather than a 3-quark formation in order to get a baryon. So you see none of that is super clean. Yeah? And there was a talk at the winter workshop this time by Peter Christensen, who is from Lund, who is close to the PYTHIA group, and you can't read it very well, but essentially his idea was that all of these string ladders that we're generating are probably the wrong way of looking at a proton-proton collision. It could be a coherent excitation of the proton that then just sends out the particles. And there were a lot of measurements of coherent production as of late in ultra-peripheral collisions. And you have to go back to getting from ultra-peripheral to peripheral, and you definitely have a way of dialing in effectively your distributions or your quark interactions more and more, which is interesting in itself. So the parton-hadron duality is effectively that you now say, if I go to low X, can the system that I'm measuring in a collision, be it a particle collision, potentially even a heavy ion collision, be completely driven by the distribution function of the gluon. And what you see also in comparison, which Dima and Thomas also have done in comparison to next to leading order calculations, you see that when you go to low X, you can effectively replace a tracing of the density matrix to just counting gluons, because the gluons are so overwhelming that you get into a region at low X, and you probably got to go beyond 10 to the -4 at least, where you really just take a Gibbs entropy and calculate the number of particles that generate that entropy. I'll come back to that. Yeah. So here the thermal behavior that I've talked about, this is an old standing problem, which we don't have to go into details about, but Beccattini first pointed out that I get the same thermal behavior in E plus E minus as I get, so this is a thermal model versus actual data, and you see pretty good agreement over many orders of magnitude. And I see this was in the Nature paper by my old colleagues, and it shows that you know, it works well. And I'm showing it because it works well all the way down to antimatter, right? Anti-collective matter, anti-helium-4, right? So you kind of wonder a little bit why these very loosely bound, very large states would survive this type of a temperature bath that you're looking at. And where does this thermalization come from in the first place? Yeah, and this is what I've talked about. There was the Snowball in Hell paper by Bromwinzing and Stachel, which didn't really give an explanation. It more or less just showed the effect. So it's still something to think about in the connection with that. And this is also the quote that Dima had, where the question now is this question that Mike asked: why would the system not be entangled if it's already starting to be in a proton? Yeah. So if you look at the idea, and the idea is now one that is three-dimensional, and I'm talking about the three-dimensionality a little bit. It needs to be three-dimensional to make it volume dependent. So you don't only want to look at the pancake and look at the transverse entanglement with the other two quarks. You want to make it longitudinal. You want to make it strings, and then have the entanglement in the moving direction also through the string fragmentation. And that potentially would make it a volume effect. And when you want to go with this into heavy ion collisions, it's got to be a volume effect. So the idea would be that in the end, the whole heavy ion volume would be entangled. And that's not so far-fetched. What's far-fetched is that it doesn't decohere through interactions in the system. So you lose entanglement if you have a lot of interactions. So the question that's being asked is whether this entropy that you measure as an entanglement entropy in the initial state can be equated to a thermodynamic entropy in the final state. Can I do a one-to-one mapping between those two? And one of the things that triggered this was experimental measurements. So Kaufman came to UH and gave a talk about this experiment where they took rubidium atoms in a Bose-Einstein condensate state. So you have a pure quantum entangled state of rubidium atoms, and then you put a disturbance in it, you quench it in a particular spot. And what happens is that when you disturb it in the particular spot, the entangled neighbors react to it. Without any interaction between the particles, the entangled neighbor essentially gives the impression that the energy distributes over the entangled volume. And it looks thermal. That means you're putting a quench into a particular point, and that quenched point distributes the energy over a larger volume. And it distributes it as far as the entanglement reaches. And then in that part of the spectrum, you measure a different temperature than in the other part of the spectrum. So you get entanglement entropy by comparing the entangled part to the non-entangled part effectively. Now, the issue was it's a very cold system, it's very few neighbors. So wanting to apply this to heavy ion or even PP collisions is a little bit far-fetched. And then 3 years later, this paper came out in Nature Communication just 2 years ago, and they addressed exactly, again, in a completely different system, as a condensed matter system, but they addressed a completely different system, a hot, strongly interacting atomic system. And it is, 10 to the 13 participating atoms. Yeah? So this is not a small system, and it's in a high temperature environment. So it's not in a condensation state, and it still maintains the entanglement in exactly the same way. So this is a very strong indicator that entanglement is not as easy to break with respect to temperature or density as people thought it might be. And it gives you essentially, they use it again for a completely different application, namely the quantum information, where entanglement is extremely important as a principle, and see whether they can use it in that sense. But it's a very interesting paper from a completely unrelated field. So here's the general idea. I think I'm going a little late. I need some big glasses. I don't know what time.
It's 1:34, but you have-
Yeah, okay. I have a few more
You're
slides.
fine because
So-
we started like at least 10, 15 minutes.
Okay. So here's the idea on let's say on the left from Dima and on the right from Flöschinger and company. So the one thing is essentially the idea of the transverse entanglement of the parton in the proton with the other two partons. If you want to look at just valence quarks, and on the right is the longitudinal idea. If you put them both together, effectively you can say entanglement entropy is an extensive quantity. It might depend on the volume. If it depends on the volume, can I use it in the same way in a Gibbs entropy, the same way I use it in an entanglement calculation? You have effectively two options. You can take the trace of the reduced density matrix in order to calculate the number of states that should be involved. Or if you go into the gluon saturation regime, you can just count the number of gluons and calculate your entropy that way. And then you want to see whether there's a one-to-one mapping between those two. So the obvious problem would be decoherence. Yeah. So essentially you cause the loss of quantum information, and you should lose it simply by increasing the temperature. The particles move more, you have more and more collisions, and typically that quantum coherence is gone. Yeah. There was, besides the experiment I showed you from Kong and company, from the Spanish and Chinese group, there was an interesting paper by Megias from Munich, where he showed that in holographic studies again, you can show that a far from equilibrium energy flow can actually survive these extreme conditions. And it's a theoretical work, though there's no proof from that. It's again this mapping of holographic systems into our actual quantum system. So it's just interesting to see that people have looked at the survivability of coherent effects in this range. Yeah. So
Maybe to ask a question.
yeah.
Do you mind going back to the slide? It seems like what you're saying is that means tracing out all the students from one of the programs.
Didn't fully understand. You have two protons.
Yeah, so you have two protons that give you one. Seems like you're tracing out all of the one of them.
What I'm doing here is I'm taking a density matrix. This is one proton. This is essentially the difference between the interacting quarks, the quark, and the non-interacting quark.
So you're taking the proton.
Taking a proton and distinguishing between the quark that interacts in the collision and the ones that don't interact in the collision. Right. So I can do this to first order by looking at in DIS. I can look at it and say I can really distinguish because I come in with a point-like probe. I know which quark interacts and I know which quark do not interact. And at that point, I can do the distinction between region A and region B in the transverse direction. If I want to do a distinction between region A and region B in the longitudinal direction, I have to go into the string generation. Does that answer? Okay. So what Dima has shown, what is important for comparing this now to experiment is that I effectively can take the entanglement entropy and I can relate it to the parton distribution function or the gluon distribution function in particular at low x. Yeah. So if this could be mapped and I am maximally entangled, then I could just say the number of states that I can calculate out of the gluon distribution function should be equal to the number of states that I can find in a thermodynamic system in the final state. Yeah? And therefore my entropy, my partition function effectively should be the same. Can I do this simply by multiplicities? And what do I have in order to look at this? What I have is effectively x, right? I can now spot this as a function of x, and I can see whether it works in a particular X range, and also whether it doesn't work in another X range. If I go away from the saturated gluon area, does it break down? So you have to have a way of measuring particle multiplicities as a function of X. Now we don't measure X, right? So we have to find a way to now describe X in a particle distribution, and the option that we have is rapidity. And I'm showing you a plot that was also in Dima's first paper that shows how you can take X and calculate it simply out of the principle that the difference between the incoming proton and the outgoing hadron gives you a measure of X. And Jamal actually gave an interesting talk about this at the winter workshop, where he says it's very likely that this simple relation will break down at large X. But since we're very interested in low X and high gluon density, this, it might hold. It is something that probably it is, in the end, it's a little too simple for what you want to calculate, but it gives you a gauge. It gives you a possibility to calculate some type of X distribution out of the measured hadron rapidity effectively. Yeah. It's very dependent on the momentum transfer scale. So you should have a dependence on the collision energy that you're looking at in the different PP interactions that we measure in ALICE and in all the LHC experiments. And one nice thing here that is kind of important here is that we measured now 6 different collisions energy in proton-proton at ALICE. So from 900 GeV all the way up to 13 TeV. So each one of them will give you a point on this X scale with a particular range. But I wasn't really so aware of this. I must admit, I'm one of these guys that never thought so much about X. And I was always told, well, if you want to measure low X, you got to go into forward direction. And I was like, okay, so we cannot measure this because we have a central detector and we have nothing else. Well, it turns out you get a nice X distribution in almost every rapidity window that you can look at the LHC. The problem is you find the low X particles together with the high X particles, and you have to worry a little about how big the ranges of particles that you measure. But the general idea is right here. If the entropy follows the parton distribution function, then as a function of X, the entropy should show a slope. Whereas if you do what you see in PYTHIA, and this is a plot from Dima and Thomas's paper, you see that this distribution should be flat as a function of X, should be X independent. Yeah? So that should be relatively easy to probe. There's a difference in the slope between the Q square. So if the Q square goes up, the slope gets steeper, and obviously the entropy goes up if the Q square goes up. But to first order, you want to first of all see whether you have a slope at all. So can I measure a slope when I just do the simple Gibbs entropy, which is essentially the sum of the probabilities that you see there on this equation. The PYTHIA one?
No, one measures with gluon and parton. The other one is the metal.
Yeah, so
different results. So how does that show the
it does not, right? That's the point. I mean, the description of the blue points essentially ignores completely any entanglement effect. That would be what you get out of the vacuum calculation. That's effectively a PYTHIA calculation. Right, I would say. Again, color reconnection will make that not flat. But that's exactly the point. I mean, what have we done? So in PP collisions, this simple mapping of the X to the Y is a little bit more complicated. I wrote it down here. There's a nice description also in the paper. You have to work with generalized negative binomial distributions to do that I'm not want to go into the details of that. I show you some examples from the Alice analysis that you can see. So here is a normalized multiplicity distribution for 13 TV data in Alice. Just to give you an example on how these things look. We have this in the CMS paper. They don't have 13 TV data, so it was interesting for us to see whether we can map to what the CMS analysis shows. Yeah. So the simple summing in order to get the entropy, that's essentially the Gibbs entropy formula. So that's thermodynamic entropy that you're calculating that way. And if you do that with the data that you measure, you'll see already that it's not flat. So you take, you get an X distribution. Out of the X distribution, you calculate the entropy distribution. This is just an example here of how this changes as a function of energy. There's also I have the same plots for different rapidity windows, and then you can see how it changes as a function of rapidity and density. But you see that the X distributions do not look very different for different energies. And this was the result.
So, you went a little too fast for me there. So you quickly said, and I agree with you that, like, of course, one rapidity measurement doesn't give you a definitive X, but somehow it gives you a broad range of X's and you're magically unfolding to one X. Like,
no, let me show you what we do. And that's probably, let me show the result that you have here. This is X in different windows. So this is the entropy, and this is the X coverage at 13 TV, for example. Now, this is 10 to the minus 3 here. So these are 10 to the minus 4, 10 to the minus 5 values. This is for plus minus 0.25. This is plus minus 5, 0.5 is a plus minus 1. So what you see is you get the mean X is almost the same, but the range is different, right? So, and when you go to larger windows, you get a larger range. When you go more forward, you get more low X, but not that much more low X. So the problem is that when you do this for plus minus 1, you have to recognize that you're mixing values in X from 0.04 times 10 to the minus 3 to 0.15 times 10 to the minus 3.
Right, that's kind of the measurement we have. And somehow you said that you had a distribution in X, whereas you've measured that.
That is that distribution.
On an event by event basis, you have a particle somewhere between whatever those numbers are, 0.1.
Yeah, but that is that distribution in X. Is that what you're saying? It's difficult that the plots are too small, but that's the same distribution. That's that X distribution. It has a mean. It has an amplitude, a mean value, but it has a range.
So then you said then I should look at the S, and clearly that's not flat, but that's one X value at the side.
That S here, if you parameterize that, you get that. So you get a distribution, an S distribution, right? So you get a probability distribution. Out of that probability distribution, you calculate the S. So you take that's the PN. You take the PN, you sum the PN for each event. And when you sum the PN for each event, you get the S distribution, and that's the S distribution on the side.
And but that as a function of X was supposed to not be flat. Wasn't that what you said was going to be our signal? The difference between falling as a function of X and flat as a function of S was S as a function of X.
Yeah.
So maybe it's just too small. My eyesight is getting bad. But like, well, how do I see that that's not flat as a function of X?
I'll show you that. Give me a second. So this is the result that CMS had. This is the result that we want to compare to. These are our X values and the range in our X values. And I think it's important to keep the range in account. And this is the S as a function of X. Now, you know, very preliminary, not fully corrected for the red data. The red data are the Alice data, the blue data are the CMS data. You see now with taking both together, you have essentially 6 different energies that you can look at. And I think when we do the right correction, the blue points will fall on top of the red points. But you see the strong S dependence on X. That's not flat, right? That's the thing that you want to see, that's not not flat on the front.
Somehow that's manipulation of the previous slide.
It's the same dot. I mean, first of all, the S here is suppressed 0. So I want to give you the wrong impression. So this goes from 1.3 to 1.9. This goes from 1.2 to 2.4. It's a factor 2. And this is the same, but you have to look at what you're looking at. So this is different energies, same eta range. Different energies, same eta range. So here you see the 3 different eta ranges. Ultimately, what you can learn from that is that the eta range doesn't matter so much, right? Where the eta range matters, and that's important here, is that the question of if you're not going low enough in X, then the next to leading order calculations do not agree with the data anymore. And that could very well be because you're not in the saturation regime. You cannot calculate your entropy just by summing the gluon states. You have to take into account that here the quark contributions will probably play a role, and you have to calculate an actual reduced density matrix to get the data. But in the lowest point, at the lowest X, and they all come out at around 10 to the minus 4 here. Now, you remember, this is 900 GeV data. So the lowest one. Here, we go further. We go to 13 TeV. So we go a little higher than this. So that 13, that's 7. 7 we both measured. Then 5 we measured. And then 2.76 and 900 CMS measured.
So why is the points at the same energy so different?
Yeah, they're different. We're still, we believe that if we do the pile-up corrections, the track cuts and everything, this is, I show that to you because you're friends.
Yeah.
This is not approved or anything. I just wanted to see whether trend-wise, we can actually reproduce what they have, namely a rather strong entropy dependence as a function of a relatively modest X change, right? But if you wanted to put a next to leading order calculation on, and Alec is just working on that, you will see that the higher you go, the more this is in agreement with what you see in a PQCD calculation. And you also see the interesting thing is when you look at the PQCD calculations, they're not agreeing with themselves so well, but they all agree in the final point. So as soon as you reach, let's say, a certain saturation point, you see that they agree with each other. So the main takeaway is qualitative, not necessarily quantitative. It is that all the data show a slope. The PQCD calculations show a slope. The PYTHIA calculations do not show a slope as a function of X. They show a slope when you put in reconnection effects and stuff.
Can that be compared to what you'll get at the EIC with electron?
Yeah, you get, so there is definitely, you're gonna hit the sky, right? You go to 10 to the minus 5 here. So you get definitely to a regime where this should work better and better, right? On the other hand, there is interesting physics in actually calculating a reduced density matrix rather than just summing over. I mean, when you sum, you make already the connection between the thermodynamic and the entanglement entropy without having really proven it. So you want to actually work with a density matrix in order to see what kind of states you're getting out of the entangled quantum system. So that's something, you know, for the next iteration.
For the first one, if there are additional effects in proton scattering, they don't exist in electron proton scattering, for example. So I wonder if it's a direct comparison.
Well, I think that like we said in the beginning, the DIS really allows you to define the matrix, right? Because you have a point-like particle hitting one proton. If you have proton-proton interaction, you have the problem that both protons have a reduced density matrix, and then you have to combine them, right? So yeah, I think EP is super important. And difference between EP and PP will then lead you to have a much better understanding of the entanglement effect. So this is at this point definitely a little hand waving here because of that. So extension of heavy ion collisions is we talked about most of this already. So the idea here is, though, in its extreme would be that the system thermalizes because of entanglement, and then any interactions that happen between the particles in the system do not decohere the system. The coherence is preserved to the final state. The interesting thing about this is that the final state would be fully entangled in that picture. That means that you have a really large volume of a quantum entangled system. And that quantum entangled system then would give you a temperature, and that temperature would essentially be the freeze-out temperature that you would get out of the thermal distribution. So you could have a system that gives you an entanglement entropy that relates to a hadron temperature as the temperature of the system.
I have a, not necessarily an issue, but it might be an issue with this because, I mean, this is assuming that you have a single volume at freeze-out. That is, you said quantum mechanically entangled all across that volume. But you and I have shown that it's possible to describe particle multiplicities outside of a single temperature, i.e. single volume picture. So what would be the actual properties or the quantum mechanical entanglement properties between two volumes at two separate freeze-outs? Is it just, it's going to be an accident then, like with this thermal behavior?
Well, let me first of all say that this goes against everything that Fernando and I have worked on in the last 5 years. That
Yeah, I
really
mean, this is-
throw the
I mean, one of them has to be right. It just,
the question that you're asking could be a good one, namely whether the color determines the entanglement volume, whether a charm entangled system looks different than a strangeness entangled system, and therefore you have different freeze-out and different volume. I don't know. I think that goes at the moment too far for me, so I don't know whether I can answer that. Certainly, when you work in a thermal picture, we have shown nice color dependencies, and I believe in them, and I think they're good. This is saying that nothing is thermal.
Yeah.
This is saying that everything is generated through a quench, and nothing is thermal. There's no thermal picture in here. And you can then ask any question about the thermal nature through elliptic flow measurements, collective measurements, thermal models, whether all of them, hydrodynamics, all of that would be driven by a quantum entangled system. So it's probably a little too far-fetched, you know.
But why do you have to carry it all the way through to the kinetic freeze out? I mean, if you make something that looks thermal via this entanglement, and then you decohere, it still looks thermal, and then Fernando is off and running with a system that's in thermal equilibrium, and that explains how it's quote born that way and thermalizes so fast. Do you have to really keep it quantum entangled for its whole lifetime?
Well, I need to have it, I think I need to have it quantum entangled until the phase transition.
Why?
Well, because the volume that you're needing in order to calculate that particular temperature is the volume of the total fireball.
Yeah, but he can kick in at some point after you use this argument to say this is how it manages to be thermalized so quickly, which we've always struggled with, that you wind the clock back and say it's instantaneous.
Well,
But then if it looks thermal and all the parts of there behaving as if they're thermal because of entanglement, and then I de-entangle, then kinematics is still the same. So I don't, they just look thermal at that point, and then it can keep expanding as a true thermal medium.
well, the differences that we measured in the freeze out was based on the charm, the quark mass, strangeness versus non-strange, which would be even stronger for the charm. So the charm would decouple first, then the strange, and then the light quarks. And I think there in thermal models, there's enough evidence for that.
Well, you could do that, or you could just say that you don't have it fully saturated, right? I mean, both those.
Yeah,
pieces
so
be
you
very
could essentially, let it be de-entangled at a high temperature, and then the rest of it is interactions.
right. That's. I mean, you don't have to have
Yeah.
an either/or
Yeah.
picture, do you?
No, I agree. I mean, I think again, it depends a little bit how you fold flavor and color dependencies into the picture, because there is a thing. I have that somewhere. I don't know. There's a Spanish group that calculated on the basis of PP. They calculated an entanglement temperature, and they got exactly the hadron temperature when they did it. But it was PP. So in PP, you can take the full volume. Right? We're also not sure whether any kind of color dependence is still there in PP compared to happy ions. I think that's a.
well, I mean, if you're assuming that it's completely driven by the charge particle multiplicity, and that is correlated, or I guess entangled to the initial state. In my opinion, it's a sort of pointless to discuss whether it comes from PP or hadron system. Because at the end of the day, what you're really replicating is a charged particle density of the system. And we can do that, easily.
Yeah. I mean, what plays into this a little bit is distinguishing initial state from final state effects, right? Because in PP, you can really nicely break out initial state effects, although I would call color reconnection already a final state effect, but you can look at MPIs compared to CR, and you can see what any model does for the initial state or for the final state. Whereas if you have a lot of final state interactions, then you run out of volume, out of room for entanglement, I would think. But it's a good point. I mean, it could be entanglement up to some temperature, and then it disentangles. One of the things that comes out of this that we've looked at, and one of the things that I have problems with, that was like a project in our group for many years, is this idea of exotic states that should be driven by a thermal distribution. So even if the system is an entangled system, but it is described by a particular temperature, then you could use that temperature in order to calculate your yields. And one of the problems was that whenever we looked for something that is similar to what was found in the charm sector, namely penta and tetra quarks in the charm sector and hexa quarks, we don't see anything. So the first study was the one from Alice on the dibaryons, which essentially goes hand in hand with any other dibaryon study that has been done by any particle collision, which shows that effectively our upper limits are about 1 or 2 orders of magnitude below the thermal model. So it is not formed with thermal model yields. It hasn't been seen, right? You can make predictions then on the basis of this, not only for hexa, penta, and tetra quarks, but also for hypernuclei, and you see what you should expect. And this is actually a big selling point for Alice 3, that with the luminosity that we can reach right now in Alice, you can make all of these hypernuclei, double hypernuclei, and so on and so on. But the question still remains, do they really follow the thermal model? So I was really puzzled that when we see penta tetra quarks in the charm sector, why don't we see them in the strange sector? And one thing we did over the last few years is we took exactly the LHCb charm channels, which were all hidden charm channels. So they had always a CC bar state in there. And we just looked at what these, instead of a P sub C, a P sub S would look like. And so it's a UUDSS or UDDSS bar. And here are the different channels that they would fall into. And you see we in Alice now measured upper limits for all of those under 2 different mass conditions. Blue and red are simply different mass conditions. And you see that they can be excluded from existence in certain cases by more than 3 orders of magnitude compared to the thermal model. So we've seen absolutely nothing in these states. And I think that's still a big puzzle. It's a puzzle that charm seems to generate them, but strangeness doesn't seem to generate them at all. And the relationship to entanglement is that to first order, these states would follow thermalization only because the system looks thermalized, but they would not follow the yield production that you would expect from a thermalized system, because they have not the same interaction cross sections that they would have in a thermalized system. And that could be a reason why you don't see them. I don't know, that's something you have to look at. And the last thing I just wanted to mention is this Rittenhouse-Brodsky paper, which makes a claim that you can make any composite object or certain composite objects through a single flux tube. And the main reason for that is diquark production. And if you have diquark as an intrinsic quantity in the wave function, then you can see how these diquarks combine when you have particular spin conditions in the string. So what they've looked at is whether a hexadiquark, for example, would be more stable than any other configuration. And they found that if you have isospin 0 diquarks, so UD diquarks, you can actually put 6 of these scalar diquarks together, and that gives you a well-bound state. Yeah. So charge 2, spin 0, baryon number 4, isospin 0 color singlet state is nothing else than a helium atom. So make a helium atom out of this. And I had some discussion at the LBNLT when Jennifer was there, and she was like, I can make all of these particles that you have on the system based on essentially combinations of diquarks. And then we looked at it a little bit, and the fact is that the hexadiquark is very stable, but the ones that you would need in order to make a deuteron or a triton, they are not stable. And I was always intrigued by, so this is the 12 Wales quark, I can read through it. I was always intrigued by that plot from one of our early discoveries, namely antimatter discoveries in nature, where you see that whether you look to the left or to the right, effectively the penalty factors when you go from a proton to a deuteron to helium-3 to helium-4 are exactly the same in matter and in antimatter. And the reason why I'm showing that to you here, if the hexadiquark would be preferred over the triton or the deuteron, then the helium-4 should go up and the helium-3 and the deuteron should go down. And that's not the case. So I think if you have the explanation how you can make helium-4 out of a single flux tube, that doesn't help you very much as long as you also make deuteron or helium-3 out of a single flux tube. So it doesn't work so well. It was exciting that she can make it in this model, but certain diquark, and all of those would be made out of diquarks, but certain diquark configurations are simply more favorable than others because of the spin combinations that we generate. So I'm not sure whether that relates at all to that. So that's all. So let me just conclude. So effectively, partons in proton collisions are entangled. And if you allow entanglement to also being transported through string formation, then you essentially entangle them transversely and longitudinal. And then the entropy becomes volume dependent and behaves effectively like a thermodynamic entropy. And that allows you to generate effectively a calculation of entropy out of a reduced density matrix. Yeah? So it looks thermal, but it's not really thermal through interactions. And if you're not having a decoherence effect through interactions, then disentanglement could survive and drive the final state particle distribution. And you can now think about this in terms of how far I can drive it in AA. I think in PP, it's on pretty solid footing based on the data that I showed you from Alice and also what Zhudun Ming and company have shown in the CMS data. So I think in AA, it's a much more difficult question because of the question of interactions and how much they lead to a decoherence. They do not necessarily need to lead to a decoherence. And that's something that one should take into account. And again, looking at that Payaris paper, they got exactly the right temperature based on just the spectrum of charged particles in proton-proton collisions. And one last thing that I wanted to mention, because Daniel is a colleague of mine and we've talked about this. So the Kansas group has written a paper on how one can make that a little bit more specific, not so much based on the large rapidity distribution of integrated multiplicity, but really looking at correlation functions, essentially angular correlation functions of dijets, and seeing whether the dynamic quantities that Keith has calculated too with DEMA based on PT spectra and Kno scaling and so on, whether these dynamic quantities could be correlated with quantum numbers that would show that you have an entangled effect, and one of them would be polarization measurement. So you could try to do a polarization measurement and do it as a function of transverse momentum, and you should see whether you see entanglement features there. I have to admit that that's a really convoluted paper that I haven't fully understood, and talking to Daniel 4 times hasn't helped much. I still don't understand it. So I'm just throwing it out there. Maybe somebody in the audience is smarter and can read it and make sense of it. Yeah. But there is some interest in doing this more on a particle by particle or color by color or flavor by flavor basis than just doing charge particle multiplicity measurements. And I think that's the interesting part of that. So I want to give thank you to the guys that work on this in my group. So there is the entanglement guy, the heavy flavor guy, and the exotic particle guy. And this looks very male dominated. So I just want to say that all the women in our group chose to work with Dr. Timmons and not with me. And I'm very sad about this, but as you know him, he's a much better looking guy, and he's also, he has that English accent, and somehow people get attracted to that. So I have to work with all the guys over here, you know about the English accent, right? They're like, so so these are the guys that worked on it, and thank you very much.
Renee, very interesting talk. We have, yeah,
Oh, yeah.
go ahead. And people in the audience also, or on Zoom, also just raise your hand, and I promise I can.
Except for Thomas and Dima, they're not allowed to ask anything.
So when you measure the initial state entropy, you basically have to know the number of gluons or partons in the initial state. So to measure that, you basically just measure like X and then extrapolate from the PDF to see what's the gluon or parton density in the.
Right. So that's a very good question, because you know, if you look at our field for the last 20 years, you know how difficult it is to measure this distribution function, which I can't find right now. This one, right? So this is one. This is MSTW. This is not even the latest one. I just put it up as an example. So you don't measure the initial gluon distribution function. You measure something that you can parameterize into the initial gluon distribution function. And obviously the uncertainty that you see in the region where it matters is the largest, right? If you want to make a measurement at 10 to the minus 4, now this is after 14 years, this is a little better now when you look at MSTW, but it still has a very large error bar. So that is one of the problems. So here, the only thing you really do is essentially doing a mapping to the mean, and then you take that mean and you calculate something out of that. So there is no, that's effectively, hopefully at some point, deep inelastic measurement, and then also spin measurement that reduces the error bar on these calculations.
And then I guess for the initial parton density also depends on the flavor. So then you'll also need to from final state jets or something, reduce the flavor of initial state, or do you just give them out?
You mean with respect to the other distribution functions that you see here? So essentially, you're going into a range where you believe that the gluon completely dominates the distribution. So you don't have to worry about the C quarks.
Oh.
And you don't have to worry about the valence quarks because you're deep enough. Now, when you're really deep enough, that's the question, right? So, are you already deep enough at 10 to the minus 3, or you need to go to 10 to the minus 4? If you wanted to put the flavor dependence into it, then you would really have to calculate the density matrices based on where you are on this plot, and which of these other distribution functions you would have to fold in order to calculate. But again, you wouldn't know, right? I mean, it's not something, because it's the initial state. So you might know the X value, but you don't know, you cannot deduce it out of the final state. You can only make a mapping.
Yes.
I have
Dimitri.
Dima.
No, oh, that's Dima.
Okay, so since Rene didn't allow me to ask
Wait, I
questions,
can't hear you.
I'll make a
I
comment.
cannot hear you,
uh,
but I see you're smiling, so don't be
Yeah, so
patient.
this was a very nice
Wait, we can't hear
talk.
you.
So I just wanted to comment on the relation between entanglement and universal temperature that we usually attribute to freeze out. So in these examples from atomic physics, which you mentioned.
Wait. Dima, start over again.
Sorry, Dima, we couldn't hear
We
you.
just hear you for the first time. Go start over.
Okay, let me start over. So I wanted to make a comment on the relation between entanglement and universal temperature that we usually attribute to freeze out. So in the examples that you mentioned from atomic physics, the temperature of the system that they have observed was actually determined by duration of the quench. So it had nothing to do with kinetic rescattering of atoms. The temperature was simply determined by duration of the quench. And the quench is, as you know, is just a rapid change of the parameters of Hamiltonian. So we have also observed this relation between duration of the quench and the temperature in a model computation of pair production by electric pulse. So I think it's quite likely that this universal freeze-out temperature that we infer from hadron abundances really has nothing to do with kinetic reinteractions, but it's just a reflection of the initial duration of the initial interaction. Then another closely related point is that the Gibbs entropy of produced system, as you said, is determined by the entanglement entropy. But once you have generated this Gibbs entropy, the system is allowed to reinteract as much as it wants. As long as the entropy does not grow, you will still have this relation. So it's not necessary to have this final state interactions absent. I mean, the system can reinteract and the entropy, can still be consistent with the initial entanglement entropy.
Yeah, I agree with both points. I mean, let me start with the second point. I mean, I'm not excluding elastic rescattering. That the point is, if you have inelastic rescattering, you would potentially change the entropy. So as long as the entropy per baryon is constant, then it's fine. Yeah. But in a chemical freeze-out picture, the entropy per baryon is only frozen at the time of chemical freezing. So the question then becomes, this is a different picture than saying the entropy is driven by the entanglement entropy of the early state and then doesn't change anymore. So
yeah, but for example, the hydrodynamical evolution at strong coupling produces very little additional entropy, right? Because, if viscosity is small and so on, then you don't really produce a lot of additional entropy. So I agree with you that the assumption would then be that you do not produce additional entropy. But this can be the case also when the interactions are very strong. So, they are separate questions. So the system can lose coherence, interactions can be very strong, but as long as you don't produce a lot of additional entropy, you would still have a relation between entanglement entropy and final state Gibbs entropy.
Okay. Yeah, with respect to the first point, I'm a little wondering about the temperature determination, because the way you say it, it depends on the duration of the quench. So in some sense, if I wanted to apply that to a particle collision, it would depend on the duration of the collision, right?
Correct.
So if I now go from a PP interaction to a heavy ion interaction, that duration should change.
Well, very little. So most likely it is, let's say, saturation momentum, 1 over saturation momentum. And so, you know, initial temperature is likely to go as proportionately to saturation momentum.
Yeah, but then it's really the initial temperature, not, let's say, the final.
Yeah, it's initial temperature which determines initial, you know, entropy of produced state. So as it should be.
Because the way the Spanish group did it, they ended up essentially with the final transition temperature as the temperature of their calculation based on quench. So there's a slight difference, and that's an interesting question, whether you can really relate the temperature to the duration, and whether you then get the initial state temperature, or if you want the final freeze-out temperature. So it's worthwhile looking into. Oh,
Okay, thank you.
thank you.
Yeah,
Thomas is up.
go ahead.
Yeah, actually, just a comment. Today seems to be Entanglement Entropy Day. So there was also essentially the hour before this talk, Renee's talk, there was a talk at the CFNS in Stony Brook, which was by Christoph Kutak, about a similar topic, about also entropy entanglement. And he calculated the entropy now in next to leading order BFKL, and he also looked on the running coupling BK. And the results are really encouraging. He seems to describe the H1 data quite well. So that's just, I put the link in case you're interested in the talk. I just put the link into the chat, so you can have a look. That's it.
There was a 2-author paper that came out. Was he one of them? It's like a Czech guy or something.
He's from the Polish Academy. It was
okay.
Martin Hanchinski and help me out, someone else.
Yeah, I think I saw their paper. Yeah, it makes the link to H1, so to the other Vera experiment.
Right. We tried in our paper, but now, of course, you know, with evolution, and that's kind of interesting.
Yeah. Yeah, I think for us, what I would say is and we can't stay probably almost completely in the PP system at the moment. One doesn't have to push this to heavy ion, because you see already so much collectivity in the high multiplicity PP system that one could really try to work out the difference between a picture like that and what PYTHIA and Herwig and so on are doing in order to describe that on a parametric level, you know, with color reconnection and so on. I had some talks with Bierlich and trying to see, for example, if you look at Agantir, this PYTHIA version that tries to describe heavy ion collisions, it drives it even further into that regime where you really try to see whether, you know, initial state interactions can in the end describe any collective effect that you're seeing in a heavy ion collision. And one should compare their parameterization with our general idea of entropy calculation and see whether there's some commonality on that. I think it would be very interesting.
Maybe a slightly ignorant question, but wave functions, quantum, all of that made me think of the disoriented power state. Do you have any thoughts on that? Is it anything connected to this? No at all.
Well, I think the point is a little bit, you have a many-body system that you have to decide at which point you have too many bodies in the many-body system so that you cannot describe them by first principle. The effect is also in the forward direction, right? So you essentially tilt your Mexican hat in a way that you're pushing the particles in a particular direction and you get a collective effect. How to connect that directly without having any chirosymmetry breaking to this, I'm not sure, you know. So essentially you're talking, because this is all, from my point of view, this is all connected to confinement, much more so than to chirality, because you're kind of working with the wave function in the confined state. Chirality is a different thing, you know, whether you can obviously not decouple it, but I don't know how to put a chiral effect into this right now. So we have a student that tries to measure it through neutral kaon versus charged kaon distribution, but I don't know what to do in order to put it into this picture.
So Renee, can you go back to that one slide where you had this, I think it was strongly coupled low temperature system and
Yeah.
Was that, first of all, there was two pieces, the top and bottom. Was that bottom part experimental or was it theoretical?
Wait, they were both experimental. There were two different experiments, in 5 different years, 2 different years.
Now, that brings up the question, all this talk about low temperature, strongly interacting, brings up the von lower bound on viscosity over entropy. Now, is there any connect? I mean, because the analogy in all of this is, you know, between the very low temperatures and strongly coupled system and the electric flow that we see in the reactor. So, other than just ringing a bell, is there any way you can use that? And also, does that translate over to a proton-proton solution?
Well, so the idea of using correlations and therefore using flow parameters, let's say, in order to determine the viscosity of the system, should definitely be sensitive to the level of entanglement. Right? And I discussed that with Keith this morning, where you effectively look at the dynamics that define shear and bulk viscosity. Now, the upper part of this does not, if you want, does not relate to that at all, to us at all. It just shows that if you have a pure quantum state, you can disturb it and the disturbance moves. But it's cold and it's few atoms. The lower part of that purposefully looks at a strongly interacting system, but it's an atomic system, right? So it's not, it's hot, but it's atomic. So it doesn't have the same degrees of freedom than what you need. And therefore it's difficult to translate that into, let's say, what a viscous effect, for example, could do to you, right? But in the end, the question would become whether any of these states that we relate to hydrodynamics right now, or you know, how strong the interaction really has to be in order to get a viscous effect, how that would translate into a system that is just entangled and therefore, you know, does not generate thermalization through interactions. Can that also show, for example, very low viscosity and all the effects that you have on the dynamic side? One should really say that at this point, everything is based on multiplicities, much more so than based on dynamics. Although one should also say that the paper from Keith and Dima looked effectively at what I call Kno scaling violations, which is effectively showing that if you measure dynamically, if you measure transverse momentum distribution, you can measure through fluctuations and cumulants potentially the level of entanglement. And then that level of entanglement would essentially be driven by how many scattering centers you have and how many particles contribute to the entanglement. Would that entangled state then be a perfect liquid? I don't know. I don't know how far you can drive it, you know. To define what?
I really thought there were two protons. There's people that use like people that do this higher level. The thing is that now that I understand that we're just doing it for that, I think like writing down this. It seems like not. I know that you like we measure some over that. If you want to compare this to the picture right now.
Yeah, I agree with you. That's why I think, reverting to essentially Gibbs entropy and taking just a number of particles is the summation of particles to get the entropy rather than the density matrix is a much easier point. And you're absolutely right. I mean, we had a conversation with a mathematician last week who worked on entanglement entropy, and he said, you're not really calculating entanglement entropy, right? Because the fact here is that when you have two regions in a very large system where the one region is entangled and the other one is not, and that interplay determines the entanglement, the trace. It determines the trace of the entangled region. That's not what we're doing, right? So if you wanted to write down the trace for based on the density matrix of this mixed state, you're really doing it on a very microscopic level. You have essentially, a few particles contributing to it. That's why, can I take a picture with 3 valence quarks and replace it with a gluon density of potentially 1,000 gluons in the same system and make that leap or not? That's not, I agree with you. It's not easy to write down the density matrix here in the way we define the system, right?
You jump to say that entropy is given by
well, yeah, so it just shows on a qualitative scale almost whether the relationship between the multiplicity of particles on the final state and the multiplicity of partons in the initial state can be matched up. Because, yeah, the picture I'm showing is a picture of 3 valence quarks. The picture I'm using is a picture of 1,000 gluons or something, right, in the same system. But again, in that same system, part of these gluons, is the one that undergoes the interaction, and the other part of those gluons is the ones that sit around and are entangled but are not part of the interaction, and that's what's meant by A and B. So it's not a reduced density matrix. It's a calculation of multiplicities on both sides, if you want. That's right.
So if I go to your plot where you showed what the entropy as a function of x is and say it's dropping.
This one or this one.
And any of them.
Yeah.
But you're changing the x by changing the square root s. Right? So how have I effectively just plotted multiplicity versus square root s?
Yeah,
And
so
said
there
one
is
of the
a
square root s, like lower energy, lower multiplicity. Ta-da.
very good point. I was hoping nobody would notice. So there are clearly effects that are trivial that you need to subtract. The one is that when you increase your rapidity range, you increase your number of particles. When you increase your energy, you increase your number of particles. In each case, you're effectively increasing the entropy because you're calculating the entropy out of the number of particles.
Right.
So the being non-linear by itself is not enough, right? So you have to, because the idea that PYTHIA is flat is really only driven by how you use PYTHIA in this case, right?
Because if you did PYTHIA here and change square root s, I assume here you actually measured really x.
No, this is EP measurement on a fixed energy.
Right, which is a very different thing than saying I'm changing x by changing square root s.
Right.
I mean, here they're
Right.
changing it, I guess, by going
Right.
forward.
So you have to some extent, when you do this comparison here, yeah, this one, for example, you have to fold out trivial effects that drive this up. But the interesting thing is if you fold out the trivial effects, the curve actually becomes potentially steeper than it is now. So you have to see which of these effects you're interested in. This is, so if you look at one of those, this is a fixed rapidity window, but a different energy. I could also take a fixed energy, but a different rapidity window, right? I can do it for one energy in different rapidities. I would get a difference in S. You can see that. It goes from, let's say, 2 to 2.5 to 3 for the same point. Yeah, there's all the same energy, but different rapidity windows. You know what I mean? It goes, this is all the same energy. This, and this. The only thing you change is rapidity, and you see the entropy goes up. Right? Okay. And then here, the entropy goes up because the energy goes up.
But my entropy is going up, is going the wrong way. When I got the wrong side, yeah?
No, this is the higher energy. You get the higher Q squared. So this is for CMS, that's a 7 TeV. Yeah? Or look at ours. I'm labeled in hours. So. Now there's a 13 TeV point. So the entropy goes up. And should go up. More energy, more particles. And then the entropy goes up as a function of eta. More entropy, more particles. Both of those are quote unquote trivial effects. So you have to take those out before you would look at that this is driven by entanglement and not driven by.
Right, so if I map around what you were just saying, because this one I find easiest to look at, and I take the left-hand one, right? So we're fixing eta. And then the highest energy is the lowest x.
Yeah,
right?
yeah.
So I'm going to make it closer to flat, aren't I? Because I'm going to pull that down somehow if I really went to that x, because I'm going forward and sat at the same energy, fewer particles at forward rapidity. I'm going to drop that dramatically if I went to that x at whatever your lowest.
So what you can do is you can take that's an x range, that's not an error bar, and you can make x windows out of it. And then you can look at it as a function of x windows, right? And then you would say it goes down because in the x window, then when you move further forward, you measure less and less particles.
Right.
Right. You're right.
But the other way you just convinced me it went up, whereas this way I'm making it flatter. And sometimes the other way you really go steeper. You have the CMS data. I'm making it flatter.
It's a convoluted plot because well, first of all, this doesn't really show you the range. It just takes the mean, which I think is a problem. You want to see the range, right? But it shows you the mean, but the mean is also changing slightly. They're not all at 10 to the minus 4. Yeah? You can see the black point there, the innermost point is at 10 to the minus, few times 10 to the minus 3. So it moves, right? It moves down in x. It goes up though, because effectively what you're doing is you're increasing the rapidity window. So the range of this point is larger. Well, what I'm trying to say, in order I agree with you that there are trivial multiplicity effects in there that you have to take out first before you make the comparison, right? And it hasn't been done yet. But so the point is that the slope parameter is something, and you see, what really the reason is that the leading order calculation, next to leading order calculation, don't capture the lower x values is not clear. It could be in part what you're saying. Okay? Effectively, we are generating a distribution that, well, that's the point. Could it be even flatter or could it be even more linear when you take out the trivial multiplicity effects?
But I guess it's trivial in that we know it goes up. In that sense, it's trivial, right? Higher energy, higher multiplicity, or larger window, but like, how can you take it out? I don't know what, don't you assume your answer to take it out? Like, you have a plan, even if you haven't managed to get there.
Yeah, you have a plan because what you do is essentially you determine you determine what you're calculating as a probability distribution, what you're summing up in order to get the entropy. So you could, for example, do this in a way that you looking at a rapidity range, but you make the range the same, just in different axes. Right, so you can look at the blue points, but so you take a 0.5, but you don't let the 0.5 go from 0 to 0.5. You let it go from 0.5 to 1. So essentially, you making sure you're sitting in a range of rapidity where the multiplicity distribution is kind of flat, but you're moving your rapidity. which is pretty true for, that's why you can do it probably potentially better in a mid-rapidity detector than in a forward rapidity detector, because you have a flatter rapidity distribution.
But if I'm at a fixed energy, the multiplicity is a measurement of the entropy. It's only because you're mixing in the changing energy changes. Then kind of sure the entropy goes up if I put more in. Is what I think of as the square root S changing, whereas that the entropy distribution is changing as a function of rapidity is more subtle physics rather than I smash more energy together, I'm going to get a higher entropy in another way. But how that entropy, once I've done it, distributes over rapidity, strikes me as a slightly different.
Yeah, so that's essentially what this is. I mean, first of all, you're trying to show where it breaks down, where it doesn't work with respect to the gluon density that you put in. And then you're trying to show whether the subtlety of the rapidity distribution has an effect. So there's many different ways of plotting this. That's why I said, if you look at just the lowest point, you can plot it for a fixed rapidity window as a function of x. You can plot it for a fixed energy as a function of rapidity. You know, it's a little bit, the plot is too convoluted to disentangle the trivial effects from the non-trivial effects. That's very different. And I agree with you. I mean, there is, you know, if you increase the energy, your entropy goes up. Has to. That's why this plot, that plot is not really that plot, right? They're not the same. This is a fixed energy, and here you change the energy. So I think the purpose, you could ask Dima, you could ask Thomas. I think the purpose of this is to show when they come together with the PQCD calculation, rather than showing the X dependence of it.
Like you provokingly showed us yours and said, look, it's definitely not keeping.
Well, what I'm trying to say is that the slope parameters are the same. We don't have the PQCD calculation. So sorry, you invited me too early. You know.
I would assume that you're maximize the separation. Is there a reason for the explanation as to why that is separation?
That it saturates?
I would assume that eventually it's going to maximize that saturation. So is there a reason that that's my assumption?
Yeah. Well, that's essentially the definition of the saturation level, right? I mean, if you reach gluon saturation, what else can drive the entropy up? So entanglement entropy, if it's driven by the gluon density at that point, at the maximal point, then what you're trying to show is not that you're reaching the maximum entropy. What you're trying to show is that you're reaching entanglement entropy, because the entanglement entropy is defined as the maximum entropy. Right. 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 I'm not sure I follow. Where could it be more entangled than Well, because effectively you're generating a system out of a single interaction, right? So you don't have more multiplicity than the maximally saturated multiplicity you can get. It cannot, I mean, this is the assumption here is that it's entangled over all states that you have. Cannot entangle more. If you don't have more states, you cannot entangle more. Again, I think that's a little bit the question of how we define entanglement compared to how people working with regions define entanglement. Yeah. Region-wise, there is really no region definition here, right? There's a definition of an interaction that happens, and a definition of the rest of the system that doesn't interact. The part of the system that doesn't interact is being treated as essentially a reservoir of states, And you say the maximum entanglement is if all these states contribute to the entropy. And that's at the saturation state. Otherwise, you cannot get more. Make sense?
Any more questions? Okay, not the, let's thank Renee.
Yeah.
Thank you.